All right, this is still section 12.1. And before we talked about confidence intervals for linear regression, now we're going to talk about hypothesis tests for linear regression regarding the slope of a regression line. You know, in the calculator, this is called a linear regression t-test, or option F, linreg t-test. Okay. Now, if we're going to do this in the calculator, we can't put sample statistics in there. We actually have to use data. Okay. So it says when the conditions for inference are met, and the conditions for linear regression is the linear. Okay. So data is linear, independent, residuals. When you plot the residuals, there's no strong outliers or skewness. Okay, the expected variances or equal variances are there, which means no triangle on your residual plot, and random data. Okay, so when those conditions are met, we can use our sample slope, okay, to construct a confidence interval for the slope, the true slope, which is beta. Okay, we can also perform a significance test to determine whether a specified or a hypothesized value of beta is plausible. Now, most of the time, this specified or hypothesized value that we're going to choose is 0. Why? Because if we have enough evidence it's not 0, then we can say that there's some sort of association. If there's some sort of slope other than 0, then we can show that the line's either going up with the positive slope or down with the negative slope. Okay. So the general hypotheses you're going to test, the null, the statement of no difference, is going to be that the true slope equals 0, or the alternative, maybe someone thinks that the true slope is greater than 0, meaning positive line, okay, positive slope line, less than 0, which means negative slope line, or not equal to 0, which means we might not know which direction the association is, but we think there is some sort of direction. Okay. So just like any other hypothesis test, okay, we take our statistic minus our parameter over the standard deviation of the statistic. So the test statistic, the t-value here, okay, we are going to take the statistic, our sample slope, minus the hypothesized value, which most of the time is going to be 0, over the standard error. Okay, and that's the same nasty standard error formula that we use in the confidence interval. Okay. And then we're going to follow the same steps, SC, CDC. We're going to go through it, we're going to compute our test statistic, and that's going to generate a p-value. And then we're going to reject the null if the p-value is less than alpha, and we're going to fail to reject if the p-value is greater than alpha. Now, going back to a previous example, now a lot of times, okay, this is one of the problems we worked on before with an interval, okay, but on a computer printout, they're usually going to give you that number right there. Guess what? It's under the T heading. This is actually the test statistic that they've already computed for us. Okay, that's the test statistic where they assume a beta of 0. So that's the null hypothesis. So they give you the test statistic, guess what? They also give you this p-value. So a lot of times that's already done for us. Okay. Now, one more thing about that, real quick, sorry about that. What they assume here on this computer printout, okay, is they're assuming that you have a two-tailed test. All right. So this p-value comes from a two-tail. So let's say this wasn't 0. If that's coming from a two-tail test, all right, So the area that they're assuming is both of those areas. If it was just a one-tail test, you would just have to get one of the sides. So you would just take whatever this p-value they give you and you would divide it by 2. So let's jump into our examples. It says, infants who cry easily may be more easily stimulated than others. This may be a sign of a higher IQ. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the children's IQ at age 3 years using the Stanford-Binet IQ test. The table below contains data from a random sample of 38 infants. Okay, so n equals 38 there. A Minitab output, the Minitab is just statistical software, is also shown. So here's the actual data. Okay. Here's the 38 pieces of data in that table, and here is the Minitab output, the statistical software output. Okay, so let's answer these questions. It says, part A, what is the equation of the least squares regression line? So I want the equation of the regression line for predicting IQ at age 3 from the number of crying peaks, or the cry count. Interpret the slope and the y-intercept of the regression line in context. So we need to give the prediction equation. We can think about it like that, or we can think about it like this. Either way is fine. Okay, I like this one personally. This is the one that they have on the formula sheet. All right. So what is the prediction? Okay. Well, here the predictor is the cry count. That's the x-axis variable. So in place of that x, I'm going to put cry count. Okay, so that's the explanatory variable. What's the other variable? It's IQ. So predicted IQ equals the y-intercept, that's this number, 91.268, plus, okay, here's the slope, 1.4929. Okay, so predicted IQ is 91.268 plus 1.4929 times cry count. It tells me to interpret the slope and the y-intercept. All right, so let's do slope first. The slope is that 1.4929. Remember, that's change in y over change in x. So in other words, it's 1.4929 over 1. So the way I would interpret this, for every increase, or for every 1 unit increase in the x variable, well, what's the x variable? It's cry count. We would predict that IQ, the y variable, increases, y increases because that's positive, by 1.4929. And you have to say predict because this is a prediction equation. So that's the meaning of the slope. And what's the meaning of the y-intercept? Okay, the y-intercept here is the 91.268. What is a y-intercept? It's the y value when the x value equals 0. So the meaning of this, if a baby did not cry, which means cry count equals 0, if a baby did not cry, we would expect the baby to have an IQ of 91.268 at age 3. Because they measured the IQs when those babies turned out to be 3 years old. Okay. So part B, it says explain what the value of S means in this setting. So they want to know what this variable represents. S equals 17.50. This is the standard deviation of the residuals. In other words, it's S of the residuals. Okay. What this means is on average, in our sample of 38 babies, let's say the average deviation from the prediction line was 17.50 IQ points. So on average, okay, if we're looking at our plot, each of these Y values, okay, each of those vertical lines, on average, it comes out to be about 17.5 units. Okay, that's how far the actual data is from the prediction data. Okay. So that's what the meaning of the standard deviation of the residuals means. On average, in our sample of 38 babies, the average deviation from the prediction line was 17.50 IQ points. Okay, in part C, it says, do these data, or I guess it should say, does this data provide convincing evidence of a positive linear relationship? So what it's asking me to do in part C, I would assume by saying there's no relationship or that the slope is 0, and I need enough evidence to show that the actual slope is greater than 0. Because if I have a slope greater than 0, positive linear relationship, that only happens when slope is greater than 0, because I also know that R is greater than 0. If R is a positive relationship, means we have positive correlation. If we have positive correlation, positive slope of the regression line. So that's what I'm trying to test in part C. Okay. So how do I actually do that? Okay. Well, I have to do a hypothesis test. So there's really not enough room on this piece of paper to do the hypothesis tests. So I'm just going to get another sheet of paper. All right. So we've got to go through our full process, SC, CDC. Number 1, statement. And part of my statement is my hypotheses, HOHA. So we're going to assume there is no relationship. And we need evidence to show that there is a positive relationship, where beta is the true slope of the population regression line of baby cry count versus IQ at age 3. So we got our statement. Step 2, conditions. Okay. These conditions are the linear conditions. All right. Let's clear that out. All right, so what I did ahead of time is I put my actual data for this into just list 7 and list 8 in my calculator. Okay, so here's the cry counts in list 7, and here's the IQs in list 8. Okay, so first thing I need to do is I need to do a scatter plot, okay, with list 7 and list 8. Now, if you're going to use list 7, you don't see L7 on your calculator's keypad. It only goes up to L6. So the way I'm going to have to do that is I'm going to have to go under my list menu, which is in blue, right above stat button, and I'm going to go down to where it says list 7. Okay, and my Y list is going to be list 8. Okay, I'm just going to do a zoom 9. A lot of data points there. And why there's so many data points? Well, there's 38 babies in this sample. Okay, so to me it kind of looks all over the place. Kind of looks all over the place. Okay. So it looks like it's slightly positive. Okay, the slope there, it does look like as I start to go up in cry count, IQs start to increase a little bit. Okay, but so I might not be convinced that the data is linear, or not, maybe not very linear. So what I can do, let me just quit out of here. Let me run the regression. So stat calc 8. All right, I'm going to use list 7 and list 8 again. Okay, now I'm going to store it in Y1. I'm going to calculate it. Okay. And just so I don't have to recalculate it again, let me just put the I'm just going to write the equation up there. I kept all the decimals in there. All right. But what does that allow me to do? Now I can do a residual plot. Okay, well, let's look at the, okay, so if I put the best fit line in there, kind of goes through the middle, as we would expect. All right, now let me turn that Y value off, and let's change this stat plot to a residual plot. So instead of doing L7 versus L8, I'm going to do L7 versus the resid. All right, and then I'm going to zoom 9 it. Okay. That is definitely random scatter. There is no pattern to that scatter whatsoever. Okay. So, since there's no scatter in this residual plot, we're okay on the linear condition. We're okay on the linear condition. I can say the residual plot shows random scatter and no pattern. Therefore, the sample data is linear. Or you could say that the scatter plot showed a slight positive relationship. We have to do independent. Okay. Is each baby independent of another baby? Yeah. As long as they weren't all in the room at the same time. But I can use this as well. All right, so I need to be n is greater than 10 times 38. It's 380. Okay. We can say there are more than 380 babies born each year. That's fine, or you can just say this is an experiment and each baby was independent of each other. And technically you don't need all this stuff because it is an experiment, so it might be better to say this. All right. And you need normal. How are we going to test normality? We actually have to look at the residuals. We have to look at a box plot of the residuals. So I'm going to come back to that because the E is the equal variances part. So as we look at this residual plot, okay, you got like one kind of high point here, but in general, it kind of looks like if I drew a line straight across, you have roughly equal variances at different levels. Okay, like if I drew a straight line straight across there, they're all about equal. If I drew a line straight across here, they're all about equal. There's no major departures, maybe other than this point. So I could say here, by examining the residual plot, you can say variances in the residuals are negligible. Okay. And I can say all residuals have we won't say that. Just say it like that a little bit. And if you wanted to make a quick sketch of the scatter plot, you could. All right, but you can just say this: by examining the residual plot, variances in the residuals are negligible. Okay. And what you can kind of do there is just kind of make a just kind of show what you know about that. They're roughly equal. And that's what I mean by lines across. Okay, we're okay on that. All right, now let's go back to the normal. Okay, we already have our residual list. It's stored automatically by the calculator. So what I can do here is I can change this plot, okay, to a modified box plot of the residuals, just of the residuals. And I can run the residuals because the regression's already been calculated. All right, and then zoom 9 that. Okay, let's do it a different color this time. Oh, okay. This might be a problem. Okay. If you think about the scatter plot we just looked at, there was one really high point. Okay, there was one really high point. That is probably that residual right there. Okay. So, all right, looking at this looks pretty good. Okay, that whisker right there, it's about the same length of that whisker, the median, pretty close to 0. This outlier is the problem. Okay, but it's only one outlier. Okay, it is only one outlier. So what I would say is box plot of the residuals I would draw it roughly the way it looks, about the same lengths of the box and the whiskers. And I would give the values roughly. All right, negative 31.13, negative 12.18 is Q1. Median is negative 2.13. Q3 is 10.87. All right. The cutoff there, or the last residual before the outlier, is 32.89. And then the outlier is 51.32. So, we need to comment on this. So which actual data point had that as the residual, the 51.32? The only way that I can really know that is, let me go back under my list here, and let me put the residuals into list 9 real quick. Let's find the one that's roughly the 58. Or no, that was 51, excuse me. Okay. It's this one. Okay, it was the 13 and 162. 13 and 162. All right. That a huge residual. All right. So the actual IQ was 51 points higher than what we would have predicted it to be. So we would have only predicted this person to have an IQ of, or this baby to have an IQ at age 3 of about 110 or so. Okay, they actually had an IQ of 162, which is incredibly smart. Okay, so we have to take care of this in some way. So I need to comment on this. I need to comment on that. First, let's make sure the data was actually correct. Make sure we didn't input that data incorrectly. Okay, let's see if we can find the 162 on here. Yeah, it's right here. That was the data point. That had such a huge IQ. All right. Now this one also had a huge IQ, but it was much higher cry count, so we would expect, let's expect that more so. Okay. So we have two options. If we have a reason, a legitimate reason to get rid of this data point, then we would get rid of it and redo our calculations and go from there. Okay, but there's really no reason. It wasn't like testing was wrong on this baby. All right, so I'm not going to get rid of it, but I am going to comment. Okay, I'm going to say, although there is one outlier, other than the outlier, the box plot of the residuals are fairly symmetric with no skewness, or no strong skewness. So I commented on the outlier, okay, but I'm still going to move forward with the test. And that's what they would want you to do. They'd want you to see that there's an outlier. It might create a problem, so the data in your sample might not quite be normal, but we're still assuming, since there's just one outlier and the rest of this graph looks pretty good, you're going to go ahead with it. Okay? You're going to go ahead with it. So you just need to comment on it. Now, if you had a whole bunch of outliers, or this wasn't symmetric at all, I would probably stop the test at that point. Okay? Because that's not, you know, if one thing's totally jacked up, if you have more than just one point, if it's an all bad graph, then I don't know a whole lot about the population. Okay. Now, in the population as a whole, if we had more data, you know, less, as a percentage, less people are going to be outliers. Here, 1 out of 38 is an outlier. Okay, if we had everybody, we're not sure if anybody would be outliers. Okay, because it's all based on on numerics and data. So I'm going to keep going with it. And then we have to do random. Okay? Looking back at our problem, says the table below contains data from a random sample. So we do have a random sample. So I'm going to say random sample stated in the problem. Okay, so that's good enough for me. Okay, that's met. We're good there. We're good there. We're good here. Here, question mark, but it's one data point out of 38. I'm still going to go forward. So that's good enough for me. So I'm going to assume sampling distribution of the sample slopes is approximately normal. So now we're on step 3, which are calculations. Okay, this is called a linear regression t-test. And since the alternative hypothesis is greater than 0, it's a one-tail t-test. So the t-value, even though it was given to us on the previous page, just as a matter of practice, I want to show you how we actually calculate that. Okay. So when we're done, we should get 3.07. So to find the t-value, we're going to take our statistic from the sample, our b-value, minus our assumed null hypothesis, our assumed parameter, which is 0. We're going to divide that by the standard error of b. Okay. So I need to figure out what SE of b is. And if you remember that formula, it was S of residuals over S of x square root of n minus 1, and S of residuals equals big square root sum of residuals squared over n minus 2. Okay, now before we start getting into calculations, I have to assume an alpha. So let's just assume an alpha of, let's just do 0.01 here. Because it's some sort of medical type intelligence connection. Okay. So let's figure out what this is first in our calculator. Now I did put the residuals in a list here themselves. Okay, I put that data into list 9, but we don't necessarily have to do that. So I'm going to take square root. I want to take a sum, so I need to go under my list menu, go over to math, and go to sum of what? Of the residuals. So I either going to go to list 9 where I put them, or I can just do the resid list. But I got to square them before I sum them over n minus 2. Well, we had 38 data points. I need to subtract 2 from that. Okay, so that's 17.4987. I'm going to say that that thing is 17.49872122. Just going to keep all the decimal places. Okay. If you notice, same number that is in the Minitab output. Okay. So that number would go under here, the 17.49872122 over, how are we going to find S of x? Well, I'm using my calculator. My x data is in list 7. It's in list 7 right there. That's where the x data is, or the cry counts. Okay, so I can do list, go to math, standard deviation of list 7. Oops. Okay, so it's putting another little sub L in there. So that's my standard deviation there, of 5.907. I need to take that and times it by the square root of n minus 1, so I have 38 minus 1 here. So the whole number there in the denominator would become 35.9315874. Okay. So if I do that number, 17.49872122 divided by that 35 point stuff, okay, that's going to be the standard error of my B. So I'm just going to save that as E for error, 0.487. So standard error of B is 0.48700100668. That's that number right there in the Minitab output. Now again, guys, if they give you the Minitab output, you don't have to do all these calculations. I'm just showing you how to do them. Okay, I'm just showing you how to do them if they did not give you the Minitab output. All right. So to find this t-value, to find this test statistic, we're going to take the sample slope. Okay, what was the sample slope? It was right up here, 1.492896598. Minus nothing over that standard error number, which is right here, 0.48700100668. Okay, so when I do that, I'm just going to put that in my calculator. I'm going to do 1.492896.598 divided by that decimal, 0.48. I'm going to get a t-value of 3.0655. Okay, if I round it. I'm just going to store this as t. Here in the Minitab output, it tells you the t-value as well, the test statistic. All right, so that's important. I'm going to need that. Now I'm going to draw it out. I'm going to draw my t-curve because I still need to find a p-value. Okay, so we're assuming the null hypothesis is that the true slope is 0. We got a sample beta of 1.49. which falls 3 standard deviations to the right on the sampling distribution. So this curve is the sampling distribution of the sample slopes. Okay, so there's a whole bunch of little b's in here that make that up. Right, now, which way do we shade? We shade based on the alternative hypothesis that it's greater than that. Okay, and this curve, this t curve, is going to have degrees of freedom of n minus 2, so 38 minus 2, or 36 degrees of freedom. This area is the p-value. So how do we calculate that in the calculator here? I'm going to go to my distributions, and I'm going to go t-CDF. All right, and I'm going to go from my t value, which I stored, all the way up to infinity, with 36 degrees of freedom. Okay, 0.00205. Now, this number is different than what's in the Minitab output. And look at what the Minitab output tells you. It tells you 0.004. That's the first time it's been incorrect. We got a number that's different. Now, why is that different? It's different because when the Minitab runs the test, it assumes a two-tailed test. So it assumes that you're getting area on both sides. So it's taking that 2%, or that 2.002 that we got, but it's assuming it's in each tail. So if you added 0.002 to another 0.002, that's how it's 0.004. But that's not the right answer. Right? This is the right answer. All right. And the whole setup shows that. All right, so let's finish out this test. Step 4. All right, would be our decision. Okay, so this p-value is really small. The p-value is less than the alpha we assumed. All right, because 0.002 is less than 0.01. So that's going to make my decision. When the p is low, we reject the hoe. And lastly, we need to conclude. There is sufficient statistical evidence at the alpha equals 0.01 level to conclude that there is a true positive relationship between baby cry count and IQ at age 3. That's my conclusion. And that wraps up that problem. A lot of steps here. And again, probably on this problem here, guys, they would not expect you to calculate this out by hand, especially since they gave you the Minitab output. Okay, they gave you all this. You could use this in the formulas. Okay, it would define the test statistic. They already even gave you that. Okay, they already gave you the test statistic. But what you would have to know what to do is on this p-value, you got to take half of it, because they assume two-tail area. We only are focusing on one tail. You have to know to half that. And one more thing on that last problem. All right, just to show you that the calculator does all this too. Okay. If you go stat and you go over to test, look at this at the bottom, linear regression t-test. Okay, so your X list is in L7, your Y list is in L8. Okay, one frequency, and we're going to assume that the beta, we're asking about beta and this other thing, row, this is a different row, so don't worry about that, is greater than 0, store the regression equation in Y1 and calculate. It should give you the same type of things. And they give you a t-value of 3.065, same thing that we got, that's this right here. Okay, it gives you a p-value of 0.00205, which is what we got, 36 degrees of freedom, and then they just give you these other parts of it. They give you the other parts of it as well, but it matches up. All right. On to the last part of this section. It says, propelled by a stream of pressurized water, jet skis and other so-called wet bikes carry from 1 to 3 people and have become one of the most popular types of RVs sold today. But critics say they're noisy, dangerous, and damaging to the environment. An article in the August 97 issue of the Journal of the AMA reported on a survey that traced emergency room visits at randomly selected hospitals nationwide. Here are data on the number of jet skis in use, the number of accidents, and the number of fatalities for the years 1987 to 1996. Okay, it says, on your calculator, make a scatter plot of the number of accidents against the number of jet skis in use. Okay, so I'm only going to be looking at this data. Okay, that's the data I'm looking at. Quantitative data with meaning. Okay, so I probably think that the number in use explains accidents, or it could even be the other way around. Number of accidents explain. No, probably not. Probably number in use explains how many accidents. So I put that on my X and that on my Y axis. Okay. So if we looked at this, let's clear out of here. Okay, I actually already put this data into, let's delete some of these lists here. I put the data into list 10 and 11 already that are in my calculator. Okay, so I'm going to make a scatter plot of L10 and L11. So turn that, let's go ahead and clear that. Scatter plot. X list is in list 10. Y list is in L11. Okay, we're doing green this time. Zoom 9. Okay. So looking at that data, that's very, very linear. Okay, it's linear. It looks like there's a linear relationship, a positive linear relationship. Okay, I'm going to say positive linear relationship. And that data looks pretty strong. There's a strong positive linear relationship. It says, formulate null and alternative hypotheses about the slope of the true regression line. State a one-sided alternative hypothesis. So what I think is that the null hypothesis is that the true slope would be 0. All right, and my alternative hypothesis is that the true slope is probably greater than 0, because if I drew a linear regression in there, a least squares regression line, it's definitely going to be positive. It says, what conditions are necessary in order to perform a linear regression significance test? Are these conditions satisfied in this situation? So it would have to meet the linear conditions. Okay, so does the data look linear? Yeah. Each year is independent of the next year. Okay, so I'm going to assume that's going to be okay. Each year can be thought of as independent data. All right. Okay, let's just assume that the residuals, if we plotted the residuals on a box plot, we'd be okay. I'm just going to make that assumption so we can finish this video up. let's just assume that there's going to be equal variances, and it does say that this is data from randomly selected hospitals. Okay, so I'm okay there. All right, and let's perform a linear regression t-test. Report the t-statistic, the degrees of freedom, and the p-value. Write your conclusion in plain language and use a significance level of 0.01. Okay, so let's do this one. Let's do this one just on the calculator. Let's do this one on the calculator. So, all right, we've already made our statement, but we should tell what the beta is. It's the true slope of the regression line. Okay. Between number in use and accidents. All right, we're just assuming that all the conditions are met so we can move forward. Okay, don't actually do that on your test. Actually think about each condition, make sure they're all good. All right, then we would get to calculations. We would get to our third step. Okay, we're not going to do this by hand. We're just going to do this on the calculator. So we're going to report the t statistic. Okay. So I'm going to go stat, test, linear regression t-test. Okay, my data is in list 10 and list 11. Okay, that's the alternative hypothesis. That's greater than 0. Store in y1, calculate. And here we go. T, very, very large T. 21.0794. Okay, p-value 1.347 times 10 to the negative 8th, or in other words, 0.00000001347. Tiny. Okay, the degrees of freedom here. Calculator even does that for us. Degrees of freedom is 8. Why? Because there's 10 points. There's 10 years of data. So it's 10 minus 2, which is 8. That's why the degrees of freedom is 8. Okay. It says, write your conclusion in plain language. So before we can make a conclusion, we have to make a decision. The alpha here was 0.01. All right, here the p-value is less than the alpha, because our p-value is essentially 0, which is less than 0.01. Okay, so we are going to reject. Our conclusion. There is sufficient statistical evidence at the 0.01 level, or at the alpha equals 0.01 level, to conclude that there is a positive association between the number of jet skis in use and the number of accidents. Reported in hospitals nationwide. Okay, so that would be our conclusion, assuming that we met all the conditions. Okay. When we do the calculations, give the name of it linear regression t-test. Okay, and if you want to give the formula, just to make sure that they're not going to dock you any points, little b minus 0 over standard error of b. And when you actually run the test in here, you can tell what b was. B was 0.00483. And SE of B is the standard deviation of the residuals over S of X times n minus 1. And you can give S of residuals. That's displayed for us here. It's 188.324. Okay. N was 38. And to find S of X, that data is in list 10, so I just have to quit list, math, standard deviation, list 10. 273922. If you give all those values, there's no way they can dock you any points, even if you use a calculator. You gave the name of it, gave the alpha level, gave the proper level, the test statistic value, you gave the p-value, gave the degrees of freedom, gave the formula, and gave all the other numerical values that generated these two. And you gave the B, gave the formula for SE of B, and the numbers used in that formula. There's no way they're going to dock you points by doing all that. They will dock you points if you don't actually write out the conditions, though, for sure. All right, that's going to do it for this note card. Sorry this one took a little while, but it's important you guys understand it. So let me know if you have any questions. Thanks.